Okay, we're live. This week we want to talk about Bayesian principles. I'd rather not talk about this, but I have to. So to review last week, we showed our claims. Actually showing this requires a fair amount of measure theory, but it can be shown that Bayes' rule continues to hold, or a version of it holds, with continuous random variable theta or multiple parameters. So theta could be like a vector. And it takes essentially the same form as it does in the case where the parameters are discrete, but the main difference being in order to obtain the denominator of Bayes' rule, you have to do an integration over the parameters rather than a summation over the parameters if the parameters were discrete. So here we're accumulating area as opposed to accumulating points in the discrete case. Each of these f's are actually different things, but they're all PDFs, and they should integrate to 1 over the parameter space, whatever that may be. Parameter space usually denoted by capital theta. And so this definite integral of the denominator of Bayes' rule, it's still the PDF or the PMF for the outcomes under the model, but irrespective of the parameters. And that integral, like, there's degrees to which integrals are doable and not, but it might not converge to a finite area. That's actually only a problem if your prior doesn't integrate to 1, which would be bad. So that can be avoided. But it will usually entail an infinite number of terms to calculate this integral exactly. Which is to say that very few of these definite integrals have elementary solutions with a finite number of terms that you could like type in on your phone. But there's a big difference between like correct, which requires an infinite number of terms, and correct to a few decimal points, which is what we're typically interested in when we're using this for research. And there's a variety of ways to get integrals correct to enough decimal points, even if it can be done symbolically. And so it's sort of, last week constituted a bit of a pivot toward the more useful case where parameters are continuous, but they're treated like random variables. Your beliefs about the parameters are getting updated, and we're going to continue that this week. But before we do that, I want to put this up again, which we did last week. It's the analysis, actually it was a Bayesian analysis, pre-registered and everything, of the BioNTech mRNA vaccine against COVID. It was developed in 2020, and they partnered with Pfizer to go through the regulatory process and then ultimately manufacture and ship it. So we can see on the left side here, the prior on theta in like aqua blue was a beta, but it seems a little weird looking here, not just because the vertical axis is in log density, but because it's so sharply increasing near theta is 0. And because of that shape, it implied this for the vaccine effectiveness. Vaccine effectiveness is 1 minus 2 theta in the numerator and 1 minus theta in the denominator. And it implied this blue distribution of prior beliefs about vaccine effectiveness before the trial started. That, as we said last week, was entirely too deferential to people who think the vaccine could be negatively effective. You're more likely to get COVID with the vaccine than without it, which there's no biological reason why that's possible. There might be a behavioral reason why that's possible, that probably needs to be acknowledged. So there was some concern that if the people in the trial might get a clue as to whether they were in the treated group or the control group based on like their arm reacting to the injection or something. And if vaccinated people thought they were safe, but actually were not safe, like the vaccine wasn't effective, but they thought it would be effective, then they might go to the club or whatever and engage in all sorts of behavior that is like more likely to get COVID. And if the vaccine doesn't actually protect them, then them thinking that they're protected may result in them taking more risk or whatever. But that behavioral thing is presumably small, you know, compared to the actual effectiveness of this. So we really shouldn't be putting so much probability that the effectiveness could be negative, but nor should we be putting such a strong prior mode on the effectiveness being nearly perfect. So this prior on theta can be interpreted as the probability of you being vaccinated given that you get COVID. And you might think that's a like weird question to ask. Like from a personal perspective, you might want to ask the question the other way around. What's the probability that you get COVID given that you're vaccinated? But that's not the question the FDA asks for, you know, whatever reasons. The way they do it here allows them to characterize vaccine effectiveness relative to an unvaccinated person. So like irrespective of the probability of getting COVID, which obviously in 2020 was quite high, you know, we're able to say, okay, you know, people who are vaccinated are half as likely to get COVID as people who are unvaccinated or something like that. And that relative comparison is what drives the decision to approve a vaccine or not. So kind of irrespective of the baseline probability of somebody getting COVID, we can say in relative terms the vaccine is this or that effective. But this prior on theta and the induced distribution on the vaccine effectiveness did a poor job of reflecting informed scientific belief at the time, which is to say during 2020, when you know, virologists and public health people and stuff like that were skeptical of mRNA vaccines, or skeptical that mRNA vaccines would work, because they by and large had not worked prior to this one and the one for Moderna. And so a better prior, or a prior that more accurately reflected scientific belief at the time, would have had very little to the left of zero, a lot slightly to the right of zero, and not so much very close to one. But the one that Pfizer chose managed to like not achieve any of that. Nevertheless, once you condition on the data, the posterior distribution of theta gets updated to this. And the posterior distribution of the vaccine effectiveness gets updated to that. And in a way that's encouraging, in the sense that even if you have these blue prior beliefs, which don't make a whole lot of sense, if you use Bayes' rule and you have a decent amount of data, and the effectiveness is like as good as it was, which was extraordinary, then you can still get a posterior distribution that is fairly precise. But, you know, there was only 94 people or whatever in the trial who got COVID. There were thousands who were in the trial, but of those, only 94 got COVID. And like 8 were vaccinated, and 86 or whatever were unvaccinated. So, you know, you saw in the media at the time, the, you know, New York Times and stuff like that saying, oh, this is 90% effective. That is, I mean, you know, New York Times has to write to a wide and not very well informed audience, but from a Bayesian perspective, the answer is the posterior distribution. The answer is, this is a beta distribution with A star and B star, where A is A plus Y and B star is B plus A minus Y. So beta distribution A star, B star is the answer. And then there's various ways of describing the properties of that beta distribution, you know, the PDF or whatever. So it might have been correct to say that the median of the posterior is 0.9, or the mean is, you know, 0.92 or something like this. But the study did not conclusively establish what theta is exactly. It just said, you know, here's the distribution that's consistent with the data in light of what you believed, or said you believed coming in. So it's not as if anyone should have been sure that the effectiveness is exactly 0.9. But that may have been the median or something of this posterior distribution. And like we said last time, the FDA has this rule that is actually mostly like for frequentist studies, but they like apply it to every drug and every vaccine and every pacemaker and stuff like that, which is to say they want the point estimate to be greater than 0.5, and they want the confidence interval to exclude 0.3. And if that happens, that they will ordinarily approve the drug or vaccine, whatever it is. Now, fortunately for the FDA, this was overwhelming. It was not a close decision by any stretch of the imagination. And if the effectiveness had been closer to 0.5, then there would have maybe been a lot more scrutiny on the appropriateness of this rule for approving vaccines. Like, maybe we should have one rule for like vaccines against pandemics, and another rule that might be more suitable for drugs that pertain to some non-contagious condition, like, you know, high blood pressure or something like that, that only affects the individual who might be taking it. But there was a lot of public health people who said, well, you know, our hospitals are overflooding with people coming in, whether it's for COVID or something else. And we don't have nearly enough doctors and nurses because they're out sick. So, you know, even something that was like 40% effective might have been worthwhile in that situation to let the hospitals like get back to normal. And so, but it was extremely expensive to roll this out. So the US government had already paid for like many million doses, even before they knew whether it would work, and that was a good investment, even though based on scientific studies previously it was unlikely to work. But the government funded a whole bunch of vaccine development efforts, some mRNA, some more traditional vaccines, in advance. It says like, here's the money, develop your thing. If it doesn't work, you get to keep the money. In order to make sure that all these places had the money to do this, and developing vaccines is very expensive. Anyway, and so if this had been a closer call, I think the rule that the FDA uses would have gotten a lot more attention. But whatever rule you want to use, you know, you can see if the posterior implies that it's, you know, satisfied or not. And it clearly was in this case. Vaccine effectiveness was at least greater than 0.7, which is fun. So what else can be said about this? Again, I always said it before, but I think it bears repeating in this situation that, according to Fisher, asking a question like, what is the probability that the vaccine is at least 30% effective, is a nonsensical question, because neither theta nor the vaccine effectiveness, which is a simple function of theta, are random variables. Probability does not apply to them. And science should not be asking questions like that, like, do you believe that the vaccine is sufficiently effective to roll it out? Make it mandatory for people who work in hospitals and like strongly recommend it for everybody else. You know, you should not be asking or using probability to answer questions like that because it can't be done objectively. It can't be done deductively. Different people are going to have different priors, and then they're going to get different answers, or different posteriors at least. And you know, science shouldn't be about what anyone like believes about the effectiveness of the vaccine. It should be about what can be objectively proven. So if you don't, but this was a vaccine developed by scientists, and it was, you know, applied for emergency approval to the FDA, which is the, you know, part of the government responsible for making decisions about whether this is sufficiently effective to justify the billions of dollars it costs to actually inject it in lots of people. And the like advisory board of the FDA is made up of scientists who voted unanimously, I think, to approve this. Might have had one person who abstained, but you know, voted pretty much unanimously to approve this. They were all scientists. And Fisher is saying science should not ask or answer this question using probability. But if you don't accept that premise, and obviously the scientists who were on the board, you know, did not accept that premise, then the past century of statistics doesn't really make sense. Because, you know, Fisher basically reacted against Bayesian statistics in the 1920s and developed his own statistics based heavily on maximum likelihood to avoid it being about anybody's beliefs, only what could be sort of objectively established. And, you know, as we talked about with the first homework with, you know, poker and whatnot, if, you know, Fisher's advice were to apply to poker the same way he was applying it to science, it would be, okay, you can only be objective about the deck because it's shuffled. So that randomization, like, we can understand and we can evaluate the implications of that, but, you know, nothing about the betting or the body language of the other players or your past history of them playing against them. All that is going to be subjective. That's you as a human thinking about how another human should be playing or has played in the past or something like that. And we can't be objective about that. So just don't use any of that information. Just, you know, go on the deck, and then, you know, you're limiting yourself a lot as to what information can be brought to bear, including in this case, like not using the information that mRNA vaccines had not been effective in the past. Like that should be relevant to the decision, but we should be open-minded enough to update our beliefs that it might work in this case, and it didn't. And whatnot. So that, I think, you know, like I said, this was the most important scientific decision of your lifetime so far, but hopefully, like, it will remain the most important scientific decision of your lifetime. And they did it Bayesian. And, like, the world didn't collapse. In fact, like, the world was actually collapsing in 2020, and the mRNA vaccines pretty much halted the collapsing and got us back on the road to normal. And this today seems like, you know, rather germane science. In which case, you know, back to the question we asked at the very beginning of the very first class, why isn't Bayesian stuff used more often? If, like, we're going to use it in the most important circumstances because it's good, like, why are we using it in a lot more circumstances that may be, you know, less life and death, literally? We can talk about that. So like I said, we're pivoting a little bit from sort of learning about the nuts and bolts of probability to starting with particularly the Lancaster reading, moving more in the direction of applying this to social science, and that gives us another opportunity to kind of take stock of where we're at. So certainly this class entails learning a lot of new things, and those things don't always build on the other quantitative classes that you've taken, and really it's more likely that what we're doing in this class is contradicting what you've learned in a bunch of the other classes that you've taken, whether that's QMSS or outside at Columbia or before or whatever. So that makes this different in a challenge. But I think we've established, and I've tried to establish, that the probability distribution of what you don't know, given what you do know, should be of interest to anyone who's doing quantitative analysis. We're going to start focusing more on social science applications, but certainly not limited to that. It's a very general, very germane thing. But not a lot of people take this class, even though it should be relevant to what they're interested in doing with quantitative methods. And honestly, some QMSS students don't know R well enough for this class, but really they should know dplyr and ggplot2 and tidyverse well enough, or like a little bit at least, regardless of this class. So that is something that you should pick up whether you were planning to use Bayesian methods or not. But the more abstract stuff that we've done, I don't think there's anything about it that is fundamentally unlearnable by QMSS students, although there's a lot of stuff to learn. What we did with discrete random variables is just arithmetic, which QMSS students should be able to do. But you need to know what needs to get multiplied together in addition to how to multiply, on a computer. And then last week we started referring to calculus in the case of continuous random variables. But we didn't actually do a single derivative or calculate a single integral. And that's in part because when that's possible, computers can do it for us. But, and a lot of times it's not possible, at least with finite number elementary operations. And so we've emphasized doing simulations because that's kind of what works in general for the rest of the weeks. And that kind of brings it back, even though it has the probability underlying it, to number crunching of many realizations of points, rather than symbolic integration. So I think there's a lot to learn, but it's not unlearnable for what we expect of QMSS students. But the way it's been going so far with the class is that master students, mostly QMSS, but some is for others, you're getting smoked by the PhD students. And you might say, well, this semester's class, the PhD students are kind of shooting fish in a barrel, but no, not really. Because, the PhD students that we have less training in quantitative methods than QMSS students do. Maybe a little bit easier for the PhD students to see how this might pertain to their research plans and whatnot, because they're probably a little bit farther along with that. But in terms of exposure to coding and other stuff that we get in the QMSS, it should be on that level. But what PhD students can do is they're really good at learning new stuff, regardless of what that is. I could be up here reading Shakespeare, and the PhD students would learn that. Well, they may not care, but if they did, they would learn that, or poetry, or whatever it is. And to do that, we need everybody, particularly those who are struggling, to be more engaged in the online platform and discussion. I would say most people are not averaging a good contribution online per week. And there's kind of a perverse relationship where the people who are doing better, learning this stuff, more questions occur to them. And the people who are struggling a bit, it's harder for them to frame questions because they don't even really know what to ask. But you've got to take the responsibility to break out of that death spiral when you don't understand something, or when one of the other people in the class doesn't understand something and they ask a question, to be able to jump in and contribute to the answer or a follow-up question or whatever. We really haven't had sustained discussion about some of the interesting things that have been raised, but moreover, there just needs to be a lot more of everything in order to learn stuff at the rate we need to learn it, in order to know all this stuff, to be able to apply it to social science problem. All right, so enough on all of that. The reading for today, particularly the Bayes rules, enumerates 3 tasks of Bayesian inference. Lancaster elaborates on each of these. 1 is estimation of parameters. 2, evaluation of hypotheses. I like evaluation better than testing when referring to Bayesian stuff. And prediction. And there's certainly other methods that involve some combination of these 3 tasks, but the Bayesian way of doing them is different, and as I would argue, better. It leads to a 4th sort of task of Bayesian inference that's more talked about at Lancaster, which is making decisions. Like, should you approve the drug? Should you call the all-in rates? Should you, make policy this or that? By making the decision that maximizes expected utility. And, we've talked about that a little bit already. So let's talk about each of these 3 and how they relate to other ways of doing quantitative methods. So here are 4 ways to estimate the parameters using Bayes' rule. There's more than 4, but these are the 4 that we have or will talk about. And it's important to keep in mind that in the situations in which these work, they're giving the same answer. The answer is the posterior distribution. And it's just a matter of how you get at that. And when you have a valid way of doing so, that kind of tells you all you really need to know. So 1 is to do analytical integration to get the denominator of Bayes' rule. But that's only possible in, I would say, around 20 situations. Tend to be fairly simple, where the prior and the likelihood are such that the integral can be done with a pen. And that's good. It really emphasizes the sequential nature of Bayesian learning, because we can say the posterior distribution is beta with shape parameters A star and B star, and A star is A plus Y, and B star is B plus A minus Y. And so that makes it explicit how each observation is, or each observation in the data that you observe and condition on is just changing the beta distribution a little bit. But if you do it all at once or one at a time, you get to the same thing either way. It's just there's so few situations, particularly with modern social science, where this is applicable to, that it's just not general enough a way to pursue Bayesian inference for estimating parameters. Second, numerical integration with quadrature, basically using little trapezoids and a whole bunch of them to get the area under the curve of the numerator, which is the denominator of Bayes' rule. That is feasible irrespective of conjugacy or anything like that. So potentially it would work with a wide number of combinations of priors and likelihoods, like it works for bowling or whatever, but it's really only feasible when there's 1 parameter, maybe 2. Anyway, this is not accurate way of computing definite integrals. when you have to do a multivariate integral across many unknown parameters. And so 2 is more general in a sense, does not require any real strong conditions about what distributions you use, but it's limited in the sense it really only applies when there's a few parameters. Third, you could draw from the joint distribution of the parameters in the outcome and keep realizations of the parameters if and only if the outcome realization matches the data that you observe. So we've done this a lot with bowling. We did it last week with the vaccine and stuff like that. I haven't emphasized this, but it should be apparent that this is only possible to do as a way of estimating the parameters when the outcome variable is discrete. And frankly, in social science, there's a lot of situations in which the outcome variable is discrete, like bowling pins or whatever. But the ability parameter or the inability parameter is continuous. So if the outcome were continuous, there's never going to be a realization that's like exactly equal to like 16 decimal points to, you know, the observed data if it were measured to. So this is not really going to work if the outcome variable is continuous. Even if the outcome variable is discrete, okay, the proportion of draws that you keep is going to be converging to the denominator of Bayes' rule. So you really need the denominator of Bayes' rule, that probability, times R, the number of times you draw from the joint distribution, to be sufficiently large. Now we've been taking like 10 million draws or whatever most of the time. But if like the probability of the observed data is 1 in a million, then you know you're only expected to keep like 10 draws. And that would be at best a noisy way to estimate like the expectation of the parameter or something. So you need the outcome to be discrete, but you also need the marginal probability of that outcome times the number of simulations to be not too small. And if you have more than a handful of data points, then the denominator of Bayes' rule, the probability of observing discrete data under the model, but irrespective of the parameters, gets really small really fast. And so this, you know, we can't really be doing like a billion simulations and so the fourth way is to do Markov chain Monte Carlo, and that's really what the 1990 papers that I keep referring to introduced, to draw from the posterior distribution directly. So this, it draws from the joint distribution of the parameters in the outcome, and then subjects them to a filtering condition to just keep some of the draws if it matches, if the outcome matches the data. But you're drawing from the joint distribution and then filtering it after the fact. What we're talking about here, which we'll do starting next week, is to draw directly from the conditional distribution of the parameters given the data, instead of drawing from the joint distribution and then imposing a condition on that afterward. So there's no, or essentially no, like, wasted draws that don't get checked. Anyway, that's going to work for any posterior distribution whose PDF is differentiable with respect to the parameters, and that's honestly most of them, although there are some, you know, exceptions to that as well. So there's other approximations and whatnot, but these are all either exact or they're exact, you know, as R goes to infinity or something like that is under our control, as opposed to some other approximations that, you know, no matter what you do, they're going to have some approximation error to them that we can't eliminate. But anyway. So as an example of parameter estimation, we can go back to this example with the mRNA vaccine. So the prior on theta, which is the probability of being vaccinated, given that you get COVID, is made up with shape parameters A and B. The likelihood is binomial with number of successes Y, size N, which is the number of people who got COVID. I think it was 94, and Y was 8. then the marginalized probability of observing 8 successes, people who were vaccinated and got COVID, who got COVID but had been vaccinated, given A, B, and N, but not theta, irrespective of theta. But still, under our model, is the joint density between theta and the outcome, purge theta with the integral, definite integral. In this case, there's like a somewhat closed form solution, even though those beta functions technically have an infinite number of terms in that product there, but we can write it in a form that looks concise and choose y, beta function in the numerator, beta function in the denominator that are offset. And so if we do this using the stuff that Pfizer had in their report, the denominator of Bayes' rule is going to be beta binomial. So we can just evaluate that with the function in the extra distro package that we used on the homework. It comes out to be 0.015 or whatever. So under the model, the probability in the prior and whatnot of seeing 8 successes out of N opportunities was quite small. We could numerically integrate the joint density, d beta, d binom, integrate that over theta from 0 to 1 with like little trapezoids or whatever. We get the same answer. We also get an error bound saying this is accurate like to at least 5 decimal points, which is like more than we need. This is fine. So even if we didn't have this analytical form, we could get by. We could have gotten by. But that hinges on only having one unknown parameter. And then if we wanted to do this by simulation, we're going to need a lot of simulations. But the proportion of draws from a binomial distribution with size n, where the success probability is a beta random variable with shape parameters a and b, that also comes out to pretty much the right answer to 4 decimal points. So we would have been okay also if we'd just done simulations. And I guess Pfizer put a whole lot of weight in their pre-registration plan on being able to have an analytical ancient solution in this case by choosing the beta prior to go with the binomial likelihood and all this. But it was kind of hard to choose a beta prior on theta that it would imply something reasonable about the vaccine effectiveness. And if you give up on the ancient solution and just have a numerical integration solution or simulation solution, then that would have freed you to choose some other prior, maybe put the prior on the vaccine effectiveness, like we did in recitation on Tuesday. And then you can more directly describe your beliefs going into it about the effectiveness of the thing. Wouldn't have had an ancient solution, but you could have easily gotten a perfectly accurate modern solution that would have comported better with scientific understanding at the time. So task 2, evaluating hypotheses. So we're evaluating hypotheses. This does not entail testing a point null hypothesis, even though the language in Bayes' rule and some Bayes' rules and some other books and articles that you might read is going to get very close to the language that frequentists use to test a point null hypothesis. They are very different things, but Bayesians have gotten in the habit of using language and otherwise like describing things to make it sound as similar as they can to a frequentist thing in order to get frequentists or people who use frequentist methods to buy into what they're doing. But mathematically it's very different. So what we mean in this case, if testing hypothesis from a Bayesian perspective means testing the research hypothesis, not testing a point null hypothesis like we would in a frequentist case. This is, usually to evaluate the probability of a hypothesis being true given the evidence. And the example of the FDA, okay, our hypothesis is that the effectiveness of the vaccine is greater than 0.3. And like, what's the probability that's true given the evidence from the trial and also what we believed going into the trial. So, what's the probability of the vaccine effectiveness being above the threshold that the FDA thinks it needs to approve the vaccine for emergency use? And so this transformation, it's easiest to just do with simulations. So we can draw from the prior, we can draw from the posterior using a different beta distribution, transform from theta to vaccine effectiveness function, and then compute the prior probability of it being greater than 0.3, and compute the posterior probability of it being greater than 3. If we do that, we would have found we're, under the prior, it was basically giving us a 50-50 chance of satisfying the FDA, which, like I said, based on what scientists thought at the time, that was exceedingly generous on Pfizer's part, and Pfizer and BioNTech. It was not the case that half of the scientists thought this would work. Guaranteed that. But the posterior probability is overwhelming. And so we would say, like, the hypothesis that this is effective enough to pass muster is true in the posterior. Yeah?
Where does the 1 minus 2 theta over 1 minus theta come from?
That's not Bayesian, that's an FDA thing.
Oh, okay.
But this is a deterministic function of theta. If theta is a random variable, this is a random variable. But it goes, okay, so theta is the probability of being vaccinated given that you get COVID. And so the VE function maps that into like the probability of you not getting COVID relative to unvaccinated people. And there's just some math reason why that works. Like I said, this might not have been the best way to evaluate stuff. There was also like, is it safe? Low side effects, other things like that. But this is what the FDA uses, and they've used it for a long time, and they use it like for every drug or whatever. So it's really not in Pfizer's interest to complain about this function. Did you have a question?
Yeah, this is more from a process perspective, but I think Lancaster applied this, and mathematically you don't have to pick the prior. You don't have to pick the prior to your data. But like from an FDA perspective, do they have to like say their prior before they see any of the data?
Yes, or at least they did. Like the prior and all that was pre-registered in this 100-page document describing the study protocol and whatnot. So, like, with your research, it's not the worst thing in the world if you, like, started to collect the data or whatever before formulating your priors. It's just, okay, your priors are for someone who believed this, before seeing the data, this is what they would believe with the posterior, after having seen it. Now, you might ask, you probably should be asking the question, why is Pfizer choosing the prior for the drug that's going to be sold by Pfizer? Like, why doesn't the FDA choose the prior? Why doesn't the FDA just say, look, Pfizer, this is how you do it? The whole thing. Or, like, why doesn't the FDA do it themselves? But that's, like, not the way it works in the United States. But, like, I didn't need to hear the CEO of Pfizer go on TV during the trial and, hype up the thing, because, they have an obvious financial interest in getting this approved. But, you know, the FDA does influence what they can do. And there was one aspect of it where the FDA told Pfizer, okay, your original draft for how this should go, like, change this.
That piece of the Lancaster reading I thought was kind of confusing, where it's like you can update your prior with the data, because it seems kind of counterintuitive to like everything we've been talking about. It's like you have some prior belief and you update that based on data. And it
Yeah.
seems like it's kind of,
Well, you can
I don't know,
certainly
maybe
update it
like
based on
rehacking or something, where you're just like
yeah,
moving
so-
things based on the data.
You don't want to be, okay, like, here's my prior, and then I like condition on the data and get the posterior distribution. And I don't really like the implications of it. So now I'm going to go back and change the prior. Lancaster didn't say to do that. He just said, you know, okay, you know, you state the prior, and it doesn't have to be what you believe. It can be what somebody else believes. Or it can be, you know, for someone who would have believed this. You know, this is what they would believe now. Yeah. So there's definitely, you can understand why pre-registration, whether Bayesian or frequentist, would be, you know, a reasonable thing to, you know, look into. Okay, good. Now, like I said, from Fisher's perspective, theta and any deterministic function of theta, like vaccine effectiveness, not random variables, unknown constants. But because they're not random variables, probability does not apply to them. And so frequentists or Fisher frequentists cannot ask questions like, what's the probability the vaccine effectiveness is below 0.3 given N and Y, which is like the complement of the question that we just asked on the previous page. Like, that's a Bayesian question. So instead, frequentists have to ask questions like, what is the probability of observing an estimate of theta that's less than or equal to 8 over n, given that the vaccine effectiveness is 0.3? And you might say, which is like correct, that just like merely stating a well-formed frequentist question makes it sound like you're having a stroke. Like, who in Starbucks would ever ask a question like of the form, what's the probability that a point estimator of this thing is less than or equal to the observed estimate that I have got, given that the answer is 0.3? But they have to put the things that are constants on the right-hand side of the conditioning bar, because you can condition on constants, but you can't treat these things as random variables. But you're taking as given something that you don't actually know to be true. It's like, well, what if the vaccine effectiveness was 0.3? And then you're asking a question about the estimator, which is a random variable. Because like every time we get in people with COVID, who is and is not vaccinated is the random process. And so if we were to repeat this trial over and over and over again, we get a distribution of the estimator of theta, and we can evaluate the CDF of that distribution at 8 over n or whatever to ask a question, you know, what's the probability of getting a more extreme estimate than what we got in the one trial that they've actually done at the time, given that the vaccine effectiveness is 0.3. But that is a very contorted way of asking a question that like just switches around everything from the way that Bayesian would ask the question. But we can simulate that. So if we invert the vaccine effectiveness function to phrase theta as a function of vaccine effectiveness, it's 1 minus vaccine effectiveness in the numerator and 2 minus vaccine effectiveness in the denominator, we can evaluate the probabilistic implications of the vaccine effectiveness being exactly 0.3. And this is how, presumably, Pfizer came up with this beta 0.71 prior, is they said, okay, well, what if vaccine effectiveness is 0.3? And then 1 minus 0.3 is 0.7. And 2 minus 0.3 is 1.7. And under the beta distribution, the expectation of theta is A divided by A plus B. So that's how they backed into an A of 0.7 and a B of 1. It was consistent with vaccine effectiveness being 0.3. Okay, let's fix that. Imagine doing R trials, like clinical trials, each of which within people who have COVID in them, and ask, what proportion of those were vaccinated. So Y over N is the maximum likelihood estimator of theta. And we can compute up the proportion of times where theta hat is less than or equal to an 8 over N, which is what we observed in the one trial that had actually been done at that point. And we get a p-value of 0 in this case. So we would reject the null hypothesis that the vaccine effectiveness is 0.3 in favor of the alternative hypothesis that the vaccine effectiveness is better than 0.3. And that is consistent with what the FDA asked for, or it would be been consistent with what the FDA asked for. But it's just a convoluted way of asking a question that has like the same words as the question, the Bayesian question that makes actual sense. Like, what's the probability that this is effective enough to get approval? Or in this case, not effective enough to get approval. So this is a much more straightforward question. And the question that frequentists ask, it just reverses everything around. Because they can't bring themselves to ask a question that makes sense in what scientists are, questions that scientists routinely ask themselves every day, every time they do a study. Like, what's the probability the treatment effect is positive? Stuff like that. But they could have done this, they didn't. And that brings us to the issue of confidence intervals. So there's kind of a weird phenomenon today where you can definitely encounter people who say, well, p-values are bad. They're opening up to like p-hacking. They're routinely misunderstood. They're not that useful even if you understand them correctly. So using a p-value to test a null hypothesis is bad. We shouldn't do that anymore. We should move beyond that. And what we should do is use confidence intervals. Confidence intervals are good, even though they're both frequentists. They're sort of different and incompatible versions of frequentists. But one correct interpretation of a confidence interval is it is a range of values such that if your null hypothesis were anywhere in that range of values, you would fail to reject the null hypothesis. So this position of a disturbingly large number of people, p-value is bad, or testing a null hypothesis using p-values is bad, confidence intervals are good, really makes no sense. Confidence intervals is just a range of values where the null hypothesis wouldn't be rejected at like 0.05 level if you make a 95% confidence interval. So another thing that is disturbing, so I mean, we all know that p-values are often misinterpreted, but confidence intervals are misinterpreted just as often, like always, basically. So a confidence interval is just a line segment. But anytime you put like an interval, people who are interpreting or misinterpreting that insist on ascribing a Bayesian topology to that thing. Like they think there's a density, okay, that integrates to 1, and then you're taking like 95% of it, and that's the confidence interval. But no, the confidence interval is just a line segment that has no third or second dimension to it. It's an interval estimator of theta, but anytime you say, okay, there's a confidence interval like between 0.1 and 0.8 or something, people are going to think, well, the midpoint of the confidence interval is like around there, it's more likely than at the endpoints. And that is not at all justified under a frequentist interpretation of confidence intervals, even though that is exactly what is correct for Bayesian posterior distributions. Like if you have a posterior density, whether you can calculate it analytically or just numerically or whatever, you can take the middle 90% of it and say like there's a 90% chance, conditional on the data, that the parameter is between here and there. But it's most likely, more likely to be toward the middle than it is toward the edges, that sort of stuff. It's all totally fine from a Bayesian perspective. And so, these Bayesian incredible intervals align almost perfectly with what people mistakenly believe about confidence intervals from a frequency perspective. So Bayesian incredible intervals is what people mistake a confidence interval for. And then they get all weird when you try to say like, the way you're thinking about it would imply you should be using Bayesian methods, not frequency. So the FDA's rule that the 95% confidence interval for the vaccine effectiveness should exclude 0.3 is, from a frequentist perspective, maybe not so attractive. It just implies there's a 2.5% chance that a vaccine whose effectiveness is 0.3 will get approved. It doesn't say anything about, doesn't say anything in particular about a situation in which the vaccine effectiveness is not 0.3, because the whole calculation leading up to it conditioned on that fact. The point of doing the trial and all this stuff, we don't really know what the vaccine effectiveness is. But we can update our beliefs about it from a Bayesian perspective using that data. And we were fortunate that it was, completely unambiguous. So confidence intervals were invented by Jerzy Neyman, who disagreed with a lot of things about Fisher, but agreed with the frequentist interpretation of probability. It's this long-run frequency. If you were to repeat this stuff over and over and over again, what's the proportion of times something happens? Namely, what's the proportion of times that the confidence interval line segment, which is going to be different every time you do a study, catches inside it, like as a net, the true parameter that you're estimating. And Neyman said, I repeatedly stated, frequency of correct results will tend to alpha, which is 1 minus the type 1 error rate, if it's like a 95% confidence interval or whatever. But consider now the case when a sample is already drawn and the calculations for the confidence intervals have given particular limits, like here and there. Can we say that in this particular case, the probability of the true value falling between these two limits is equal to alpha? The answer is obviously in the negative. The parameter is an unknown constant and no probability statement concerning its value may be made. But the pro-confidence interval cult today is like, we love confidence intervals. It's so great that Neyman created these confidence intervals for us because we can use them to describe a range of values that are compatible with the data. But Neyman also said, you people have your head up your ass. And we're just going to ignore that part of this statement and do, what we do with the confidence intervals. So it is, if the confidence interval for the vaccine or whatever effectiveness excludes 0.3 or not, that does not justify saying anything along the lines that there's a 95% probability or whatever that the vaccine effectiveness is greater than 0.3. Because that is a calculation involving one realization of a random variable, whereas the confidence interval concept pertains to what if we were to do this over and over and over again. And we get different confidence intervals every time. Among all possible data sets that could have been drawn from a population with characterized by parameter theta, like what proportion of the time would we get it in our net? But that's not how most people use confidence intervals today. They basically pretend that they're Bayesian incredible intervals and then go on from there. Now, Neyman was much less overtly hostile to Bayesian stuff than Fisher was. If you read Neyman's other papers or whatever, he just says, okay, what I'm doing is totally different and incompatible with what the Bayesians are doing. But no, like, Bayesians are evil, of the sort of things that Fisher said over and over and over again. He just said, you know, what I'm doing is different. And, you know, it is. But I don't think it's as good as what the Bayesian stuff gives you, particularly with the modern way of being able to do computations that became available to us starting in 1990, but was not remotely available to Fisher and Neyman in the 1930s when confidence intervals come. So third task, prediction. So from a Bayesian perspective, prediction is just the outcome margin of the joint distribution between the parameters and the outcome. Or there could be multiple outcomes, whatever. You could use either posterior or prior draws in that joint distribution. Obviously, your posterior ones are going to be more precise because they've conditioned on the data, but really we're just talking about a marginal distribution of the data irrespective of the parameters under the model. But the model could be either updated or not based on it. So, you know, we can simulate this as well. Draw from the prior, draw from the posterior, draw predictions from the prior, draw predictions induced by the posterior. And we can see in this case, and it's kind of a weird calculation, but the proportion of times where the posterior prediction of the number of people who were vaccinated given that they got COVID being less under the posterior than under the prior is actually only 80% because the prior was so weird and it put so much probability on it being like a prior mode on the vaccine effectiveness being close to 1. So even though like our beliefs about theta have changed a lot as a result of it, you know, you can still get, I think, not great prior predictions because of how bad the prior was. Now, this is the Bayesian version of prediction. So we're defining a marginal distribution over outcomes after purging the parameters. Other people tend to use the word prediction to mean prediction induced by a point estimate of theta, rather than the distribution induced by distribution of theta conditional on the prior and the data. So when we say prediction, we're talking about a predicted distribution. When other people say prediction, they usually mean like one number. And that's not so good. So like we've said before, this whole idea of like conditional probability distribution of what you don't know given what you do know includes the widely considered situation, particularly with like business analytics or whatever, of predicting the future given the past. So what is the distribution of a future y, so that n plus 1 y, given past y, y1 to yn? And to obtain that, Bayesians do what I refer to as the hokey pokey. No one else calls it that. However, we obtain this distribution of the future given the past by putting theta in and integrating it out. And you can like shake it around and like do the dance or whatever if you want to, but put theta in. So joint distribution of future outcome and theta, conditional on past outcomes. And we're going to purge theta out by doing an integral over the space of theta. So in writing this as the conditional PDF of future outcome given theta times posterior PDF of theta given past theta and like the priors and all that too. And then integrating out theta to leave a PDF for the future given the past. And in the case of the BioNTech vaccine, this can be done, this integral can be done analytically. We get the probability of someone who has COVID being vaccinated, just like one person who has COVID. What's the probability they're vaccinated? It would be like 9%. And so that, you know, that sort of calculation can certainly be useful, but it's not done that much at all by people who purport to be interested in the future given the past. Because such people these days tend to be infatuated with supervised learning techniques. And the supervised learning techniques that they're fascinated with eschew probabilistic thinking. So instead they'll reason something like this: okay, we get some point estimate of theta that's like y over n, or maybe we like shrink it, or you know, something like that. We get some point estimate of theta, and then the probability of a future person being vaccinated given that they have COVID and theta hat. Well, that's just the binomial, or it's really Bernoulli, because we're just talking about 1% now. Special case of binomial. So the probability of that is just theta hat. Theta hat being y over n in this case, that's much less than a half. So we're going to classify the n plus 1 person as being 0 or unvaccinated, deterministically. There's no uncertainty about the classifications. It's just, well, the classifications might be wrong with some false negative rate. And then there's also some false positive rate. And then with those you can calculate like sensitivity and specificity and like all kinds of other stuff. And you might say, well, you know, dealing with probability is hard, makes things complicated. What's so bad about, okay, like we're classifying this as 0 and then we have like a 9% false negative rate? Well, you don't have a 9% false negative. This calculation is over all possible values of theta, weighted by their posterior density. This calculation is conditional on theta being one number, not weighted over all the numbers that theta could be. And as we said, like on the beginning slide, the trial did not establish exactly what theta is. They only had 94 people who got COVID in their thing. Like, how could that possibly establish certainty about what theta is? So here, we're averaging over what theta could be using the posterior PDF as the weight function to get the integral, in this case, that comes out to this. This is just conditioning on one value of theta as if it were the truth, when it's only a point estimate of the truth. And as a result, because of the, I'm not going to go back to it, but well, I could, the skewness of this distribution. So the posterior distribution of theta is a bit skewed here. So, you know, the one most likely value or whatever is lower than the average value. And so if we condition on like 1 point, that's more optimistic than what theta is on average. And so we're, in this calculation that I was talking about, the conditions on theta. This is a more optimistic estimate than like the posterior mean of theta. And it's certainly more optimistic than averaging over all possible values of theta, weighting them by their posterior density. And so the false negative rate induced by this is going to be higher than 0.9. Now, it would still be on the low side, but this is misleading as to what the false negative rate is, because it assumes theta is known, rather than utilizing probability to average over the distribution of theta with appropriate weighting. And like I said, even when the supervised learning people might refer to probability, it's always conditional probability of data given point estimate. They're not using probability in the estimator like we do when we get these posterior distributions. Does everybody understand that difference? So, I mean, supervised learning, they definitely see themselves as doing something very different from traditional statistics, by which they mean frequentist statistics. And there are differences, mostly because the supervised learning people just skip all the hypothesis testing stuff. And because they're interested in prediction, which wasn't really on Fisher's radar that much, you know, they can use like slightly different functions, like penalize likelihood and stuff like that to get better predictions. But from a Bayesian perspective, they're both supervised learning and traditional frequentist stuff are very similar in that they're plugging in point estimates when really we're far from certain as to what those parameters are, given the data that we have. Now, a rationalization for doing what supervised learning people do is to say, well, these things are intended for situations in which you have big data. In which case, if you have big data and a very simple model, then there would be negligible uncertainty about what theta is, even if you were to do like a fully Bayesian thing. In which case, like maybe the fully Bayesian thing isn't really worthwhile. If it means like everybody would have to actually learn probability and like do priors and all this other stuff. You know, if we're only going to do this in situations where we have big data and simple models, in which case the posterior uncertainty, even if we were to do it right, is just minuscule, then maybe this wouldn't be so bad. But people then go on to apply these supervised learning things, irrespective of how big their big data is and how complicated their model is. And most of the things in the social science, or science more generally, are much smaller than what these tech CEO people would consider to be big data. Like everyone who has a Facebook account, big data. As opposed to like what, you know, the Pfizer people were dealing with, you know, 100 or maybe 1,000 people or whatever in the trial. That's well within the realm of small data analysis. Okay, another probability distribution, the gamma distribution, which is defined on a sample space of the non-negative real numbers. It also has shape parameter, or shape A parameter and rate B. So these, even though I use A and B for them, they don't have much of a connection to the A and the B and the beta distribution. So like every distribution you have to just sort of consider on its own, even though there actually is kind of a relationship. But anyway, the PDF of a gamma random variable, so this is for a continuous random variable x, is given by this expression here, where the so-called gamma function is the integral from 0 to infinity of t to the a minus 1 times e to the negative t, integrated over t. And this also does not have an elementary solution, but it can be expressed as an infinite product, or a product of an infinite number of terms. And the gamma distribution for positive real numbers a can be thought of as a continuous generalization of the factorial function for positive integers. Namely, gamma of a is equal to a minus 1 factorial if a happens to be a positive integer. But the gamma function is valid for any positive a. Could be continuous. Whereas factorial function is only defined for n. But this gamma function ensures that the PDF for the gamma distribution integrates to 1 over all values of x in the sample space, which are all of the values. Moreover, we can see that if a is exactly 1, the gamma PDF simplifies to that of the exponential distribution with rate b. So that goes away, that just becomes b. Gamma of 1 is 1, and so we're left with just this piece over here, which is what we saw last time to be the PDF of the exponential distribution with rate b, and consequently with expectation 1 over b. So exponential special case of gamma. You could use the gamma distribution when you have more information than just the expectation. So exponential is maximum entropy, so in a manner of speaking, optimal. If the only thing you know about the random variable is it's positive and you know what its expectation is, the distribution closest to uniform that's consistent with those constraints is exponential. But if you know something more than the, or you believe something more than the expectation, then the gamma gives you two hyperparameters, a and b, with which to reflect your beliefs. And it can be shown, although I don't show it here, that the expectation of a gamma random variable is a over b, and the variance is a over b squared. So we can use those two facts when we're using this as a prior to reason backwards, or it's not backwards like wrong, but in reverse order. So start by thinking, okay, what do I think is the expectation and the variance of this positive random variable? And then I can express A and B in terms of mu and sigma squared in order to figure out what A and B need to be. So if I think this has like an expectation of 3 and a variance of 6 or whatever, I can plug those in and figure out what A and B are consistent with that. And then use that with my product. And we're going to use the gamma, so we're going to use the gamma prior in this situation. So suppose that x is discrete, it's a count, and it's distributed Poisson with unknown expectation mu. And we have a gamma prior on mu with shape A and rate B. What is the marginalized distribution of x under our model, but irrespective of mu? So what's the probability of the count being x conditional on A and B, but not mu? Well, we form the joint density between mu and x, conditional on A and B, purge mu by integrating over it, And the integral, if you remember what was on the previous slide about the things in this form, comes out to this. Which, like I say, you never need to memorize these things. You can always look them up. This is a version of the probability mass function of the so-called negative binomial distribution. And unfortunately, the negative binomial distribution is probably the most confusing distribution out there. So one, like, why is it called negative binomial? Like, x is positive, like, or non-negative, like, how could it be negative binomial? This way of motivating the negative binomial distribution does not motivate the name. So this is like a Bayesian way of deriving that negative binomial distribution, in which case a better name for this would be Poisson gamma, like, or gamma Poisson. Like when we do beta binomial, like the prior is beta and the likelihood is binomial, and then we integrate out the success probability to get the denominator of Bayes' rule, and that's called the beta binomial distribution. And that's at least like a name that makes sense. In this case, you would say this is the gamma Poisson distribution. But it's not called that. It's called negative binomial, and negative binomial has like 10 different parameterizations that all kind of imply the same thing, and this is only one of them, and it's not even the one used by R. So this is kind of a mess, but this integral is somewhat doable analytically, even though it involves special functions that have an infinite number of terms to compute. So anyway, don't get too hung up on this, but this is like the denominator of Bayes' rule when we get the posterior distribution of mu. So let's say we have realized counts, data, x1 through xn, that are presumed conditionally independent Poisson realizations with expectation mu. Under our prior, gamma prior, for mu, the posterior PDF is like this. So density of mu given A and B and all the x's. We've got a prior, in this case gamma prior, for mu. And we've got the probability of observing all these conditional independent x's. And so because they're conditionally independent, we are in a special case of the general multiplication rule, where we can just like multiply them together. There's no dependence of like x2 on x1 that we have to worry about. Conditional on mu, the x's are conditionally assumed to be conditionally independent. We can just multiply them all up together to get the probability of observing the whole data set, given mu. And then in the denominator, we have the probability of observing the data set conditional on A and B, but not mu, which would be a product of the negative binomial things on the previous slide. So this one is kind of doable. The way in which is the shortest route to doing it involves observing that, okay, if we write this, this is the Poisson PMF here for x of n. We can simplify this, so we've got e to the negative mu n times, but this doesn't involve x. So it can go on the outside, but there's n of them, so it's now e to the negative n times n. And we've got mu raised to the power xn, but we've got capital N of those. So that can also come on the outside, and it's using the rules of arithmetic with powers. It's mu raised to the power, the sum of the x's. And then we're left with this 1 over xn factorial business in the denominator. So if we let s be that sum in the numerator, let's say ignore that part and say this is s right now. We'll see this is in the form of a Poisson for s, which is the sum. So it can be shown, and this is true, that the sum of the data is distributed Poisson with expectation n mu, if the x's are all individually distributed Poisson with expectation u. And so then we can ask the equivalent question what is the posterior distribution of mu given A, B, and S? And ignoring constants, which we're allowed to do, Lancaster does this a bunch. We have this stuff from the prior, and then we have this stuff for the likelihood of S. We group terms together, and we see this is mu raised to the power A star minus 1 times E raised to the power negative B star times mu, which is proportional, or is the kernel of a gamma PDF with shape A star, A plus S, and rate B star, B plus A. So this is another example of conjugacy between the gamma prior and the Poisson likelihood. Gamma prior is kind of a miracle in that it is conjugate with a bunch of different likelihoods. So like these analytical calculations are doable the ancient way. They're totally doable the modern way as well. Those are, but it is doable the ancient way, and that was the priority back in the day before computers were able to do the modern calculations. And so the posterior predictive distribution implied by this is going to also be negative binomial, but with updated parameters A star and B star, rather than the prior hyperparameters. So this is very much along the lines of, beta and binomial, except now we're in a situation in which the data are unrestricted counts. There's no upper bound on them. And consequently, the expectation is just some positive real number without, being bounded between 0 and 1 over. But in this still relatively simple case, just one parameter. All the cases, almost all the cases really, where we can do the calculations the ancient way, involve situations in which there's only one unknown parameter, which is not representative of what science usually is doing when they're modeling, some phenomenon, any phenomenon really, that inclusive of one counts. Any questions about this? All right. So like I said, we can do it the modern way. Let's say we have 5 observations. Still not big data. Little data. Say we start with an A of 1.6 and a B of 0.8 and do like 1 million simulations. And let's suppose that we observe a sum of the data points that's 20. So the 5 data points sum to 20. Simulate from a gamma prior from mu. Do the calculations row by row, where we draw 5 from a Poisson with the realization of mu, sum them up to get S. Then after we're done doing that for all million realizations, we're going to filter to the ones that entail S being 20, supposing we observed in the actual data that the sum of the Poisson's realizations was 20. And then we can estimate the expectation, or we can calculate it exactly, or we can estimate the marginal by seeing the proportion that we keep, or we can integrate it numerically with little trapezoids, and we get to 2 digits at least, exactly the same number here, and here it's like off in the 3rd decimal point, whatever. But you can see only 1.5% of the draws got accepted. So we had to start with 1 million in order to end up with 15,000. Now 15,000 is plenty, but it seems not great that we had to start with 1 million in order to end up with 15,000. And this was just with 5 data points. What if we had slightly bigger data, like 50? The probability of observing 50 random variables that come out to exactly what they come out to would be some tiny, 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 tiny number. And so we'd have to start with like 1 trillion in order to end up with 10,000 or whatever. And that's not going to be sustainable sorts of data sets that whose sizes we encounter in the social sciences. So starting next week, we're going to have to learn another way to do stuff. But we can draw from a negative binomial distribution. We have to make an adjustment to use one of the parameterizations of the negative binomial that's supported by R. And so we can get a prediction for the next count. One realization from the posterior predictive distribution, and it comes out to be 1. So given our updated A star and B star beliefs about mu, the first realization from the posterior predictive distribution in the modern way, came out to be 1, but we usually wouldn't just take like one realization from a posterior predictive distribution. We would take thousands or millions or something like that, and so we'd have a whole distribution that would, give us the probabilities of that, but we could obviously just compute them from a negative binomial or from this, but using A star and B star. So that's the prior, but we could update it to A star and B star. So these predictive distributions, you can and should think of them as distributions of belief about the outcome. But when people say like priors and whatnot, they're usually referring to beliefs about the parameters. But your beliefs about the outcomes are implied by your model in its entirety, including the parameters and like what distribution you want to use for the outcomes given the parameters and whatnot. So one way in which you can check that your prior distributions seem reasonable is, does your prior distribution induce a reasonable prior predictive distribution of the outcome? And as we'll see, but after spring break, a way to check that your model is reasonable is, does the posterior predictive distribution of the outcome resemble the outcomes that you actually observe? Like a model fitting checking procedure. We'll get to that. Okay, we simulated. So good part of Lancaster reading talks about some principles to choose priors with, and it kind of goes down some rabbit holes that I wouldn't have. So one, Lancaster mentions improper priors. And that means a prior distribution that does not integrate to 1 over the parameter space. So the integral doesn't converge or not to a finite number. I would say don't use those. If you use a proper prior, one who integrates to 1 over the whole parameter space, it guarantees the posterior distribution is also going to be proper. It integrates. If you use the improper prior, you have no guarantee, and you have to work it out on a case-by-case basis as to whether the posterior distribution is going to be proper or not. It's never obvious just by like glancing at it. You have to do some fairly serious math with like a pen in order to figure out if your posterior is going to be proper if it's induced by improper prior. So that's why I would say just avoid improper priors, only use proper priors, those that integrate to 1, and that's a sufficient condition for the posterior distribution being proper as well. Now, improper priors are historically used a lot, even though I would recommend against them. And that has sort of fed a misperception that improper priors are uninformative, which is not true. One, they're not proper, so they're not even coherent probability distributions. It's basically saying you're not even starting with a coherent set of beliefs. But secondarily, so like you can say, the normal distribution becomes improper as sigma goes to infinity, or something like that in the limit as sigma goes to infinity. And people say, oh, well, okay, this is a very, very uninformative normal distribution. But that conveys, that quote-unquote uninformative prior distribution conveys the information that all real numbers are equally plausible for this parameter. Even numbers that your computer can't even represent. So like the range of numbers that a computer can handle is something like 10 to the 308. But all real numbers goes way beyond that in both directions. Also, a computer can't like represent every real number even within its range. It can only represent like a small number of actually rational numbers. So this improper prior business, particularly over the whole real line, is non-informative but conveys the information all real numbers are equally plausible, which is information, but that usually does not make sense. Do you really want to say like some number that's bigger than 10 to the 300th is just as plausible as 0 if we're talking about like a treatment effect for a drug or whatever? So in almost all cases of science, definitely social science, smaller numbers are more plausible than bigger numbers. I don't even care what the model is. Like the fact that a social scientist is doing it implies that, you know, human-sized numbers are much more plausible than like numbers that humans don't even encounter. Like off the top of your head, like what number comes after trillion? It goes million, billion, trillion, and what? Okay, you happen to get that right. But I guarantee you most people would not know that quadrillion comes after trillion, because humans never deal with quadrillion anything. Like trillions is kind of the units for like GDP of a big country. And that's like the biggest number that a social scientist ever needs to deal with. Like US GDP is like 20 trillion, maybe a little more. But nothing in social science is a quadrillion or more. And most things are a lot less. Like your income, even your student debt, it's a lot less than a quadrillion. And so those sorts of numbers, models involving those kind of concepts are going to involve parameters that have much closer to 0 distributions than the idea it could be any real number. So then another principle is basically just say what you believe, subjective priors. All the priors are subjective, but maybe weakly informative priors are more subjective in the sense that you want it to be like somewhere close to 0, but entertaining, at least there's a small possibility that it could be decent ways away from 0. We've talked about entropy maximization as a way of choosing prior distributions that have the least information beyond the constraints that you put on it, like it's positive and it has an expectation or something like that. Lancaster talks about Jeffreys priors, which are invariant to reparameterization. And this is maybe more, it sounds more appealing than it is. So Jeffreys was great. In the 1930s, the only person who would tell Fisher to go like jump in the English Channel was Jeffreys. And he pretty much held it down on behalf of Bayesians for like a decade. In the face of being drastically outnumbered by Fisher's minions. But Jeffreys wrote a book which is almost impossible to read and had some other weird ideas. And this one, I think, in the case of a scaling parameter, kind of makes sense. Like, your beliefs about a parameter should be the same whether it's in units of dollars or units of euros or whatever other currency, because it's sort of arbitrary as to what those units are. And you might want to choose a prior that has the same amount of information irrespective of the units. So the non-informative prior that conveys the information that the units are arbitrary and don't substantively tell us anything. But Jeffreys priors are also used in other situations in which it doesn't make as much sense. The amount of information being conveyed is irrespective of how you might transform the parameters. So in a lot of other cases, the units or how you transform the parameters is an important part of the model, and you should be reflecting your prior beliefs in those terms rather than saying, you know, let's come up with something where the transformation doesn't matter. Fifth, objective priors. So objective priors are still subjective. But objective prior, people who use this phrase say, well, how can we choose the prior that has expected to have the least influence on the posterior across all possible data sets that we could observe? So it's kind of a frequentist-ish way of thinking about priors, but it doesn't mean Fisher likes them. They're still subjective. Everything is. So overall, I would say choose a prior that integrates to one, so it's proper. And then try to choose hyperparameters or distribution that are consistent with your beliefs. Don't get too hung up on does this prior like exactly reflect the totality of your beliefs. It just needs to be, particularly, you know, in the models that we've been talking about, roughly consistent with what you believe. Like if it matches the mean and the variance, like that's good. And really, and this is kind of counter to what people usually think. The important part of a prior is what it puts negligible probability on. So there's negligible probability that this drug is going to make you live to be 130. More so than, okay, what is like likely under the prior. Because most priors are such that when you update them with the data, like that part of it is easy to move. And so we're basically using priors to say, okay, here's like a reasonable set of values, and then we're going to update within that. You got to take a position on what in your model, the degree of reasonableness of parameter value might have. And like I was saying before, if you want to check whether your priors are reasonable, you can see, even before you've gotten the data, whether the prior predictive distribution of the data seems reasonable, and if so, your priors on the parameters must have been reasonable as well, and if not, you can go back and change your priors, because you haven't gotten the data yet, and make those result in a more reasonable distribution. So Lancaster also gets into the weeds on the likelihood function, and this came up like the first week, and I said, you all are obsessing about this too much at the time. So it's the same expression as a PDF or a PMF, but with three distinctions. One, if we have f of x given theta, we're thinking of x as the random variable and theta as given. Whereas with the likelihood function, it's the same expression, but we're considering it to be a function in the mathematical sense of theta that is only to be evaluated at the observed data and nothing else. So these integrate to one if it's continuous, or they sum to one over the sample space of x if it's discrete. Whereas if we integrate the likelihood function, and this would ordinarily be a multivariate integral over all the different thetas, that integral may not even converge, and even if it does, it's not going to be one. So likelihood functions don't define a PDF with respect to the parameters. Also, we usually don't think about the likelihood contribution of like one individual data point. It's going to be for conditionally independent data points, all the contributions multiplied together. And that is not particularly numerically stable. So it's kind of fine if you're doing this with a pen. But if you're doing this on a computer, what is more useful is the so-called log likelihood function, where we take the natural logarithm of the likelihood function. And the action of the logarithm on a product is to turn it into a sum of logarithms of positive numbers. And that is much more amenable to numerical calculation on a computer than this is. But because it's like universally used on a computer, people just say log likelihood, or say likelihood when they really mean log likelihood. But one thing that might give you, some optimism is that Bayesians can, they don't have to, but they certainly can use exactly the same log likelihood functions as frequentist. Now, you could depart. There's a lot of things you can do as a Bayesian that are not really feasible in terms of models that you could estimate as a frequentist, but there's certainly probably too much of just, oh, okay, other people who are frequentists are using like Poisson likelihood, so I'll use it. Instead of thinking about, okay, well, maybe something else would be better. But you can use literally the same log likelihood functions that the frequentists do. But first, let's illustrate this likelihood PDF phenomenon. So let's say we have this expression here. And for a given mu and sigma, this expression is a PDF of x, meaning it integrates to 1 over all the real numbers. And we can verify that basically with numerical integration in R, saying, okay, fix sigma to be 2 and fix mu to be 1, integrated from negative infinity to infinity, the normal PDF, we get 1, as close as it can get. But for a given x and mu, the integral of this expression here over the positive real numbers is a likelihood function of sigma. But this integral with respect to sigma diverges. Like if you try this in R, even if you increase the accuracy, you get extremely bad integrand behavior, which is R lingo for this doesn't converge. And it doesn't. Like that's true. So Fisher especially had to be precise, and if you have an expression like this, well, is it a function of x or is it a function of the parameters? And that changes how we interpret it, but we should not interpret likelihood functions of parameters as probability distributions. But we can use them, or not us, but Fisher, use them for maximum likelihood estimation. So, they don't allow prior on theta, because it's not a random variable. If there's no prior on theta, there's no joint distribution of theta in the outcome, and so there's no marginal distribution of the outcome, and so there's no conditional distribution of theta given the outcome. None of that, because you're not allowed to have priors. Those are subjective. But you are allowed to condition on theta, or to consider how the probability, maybe density of a continuous y changes as a function of theta. And since logarithm is a monotonic transformation, the value of theta that maximizes the likelihood is also the value of theta that maximizes the log likelihood. And that's much more amenable to numerical maximization on a computer to find that value of theta. Okay, out of time, so pack up your stuff and get out. And we'll post the second homework tonight. It'll be due before class next Thursday. And we'll have recitation office hours as usual on Tuesday, which will give you some more practice with this stuff. Okie dokie.